Thank you very much for the invitation and for the nice introduction. Thank you for coming. So in today's talk, I would like to tell you a bit about what I do and what I'm passionate about, which is really to look into the secrets of the building blocks that make up everything we see, and to understand how maths is really a compass to guide us into the journey towards what we still do not know. So let me first tell you, I will start by saying, what I do. So what is my job as a phenomenologist, this word that Jeffrey mentioned at the beginning. And then I will tell you why, some of the highlights of our life as particle physics phenomenologists was the discovery of the Higgs boson. So what is the significance of the discovery of the Higgs boson, and why we need some physics beyond the standard model of particle physics. And then I'll tell you a bit about two things that we have, two mathematical concepts that help us understanding what is beyond what we already know, which is, on the one hand, the concept of symmetry, on the other hand, the concept of effective field theories, okay? So what are the big questions of particle physics? The question is simple, if you want, what are the elementary particles? So what are the building blocks of everything we see, and what are the forces that make them interact with each other, okay? So that's the idea. And clearly, the farther, so if you want to see like a molecule or like a cell, a molecule, you can use a powerful microscope. You can even use optic microscope to look into the atom. But if you want to go subnuclear, so if you want to see the nucleus of the atom or what lies inside the nucleus of the atom, we don't have powerful traditional microscopes. So what we need to do is to smash particles against each other, which is the idea of particle colliders, which is like when kids smash little cars against the others, so they break into pieces and they understand what they're made of, okay? So that's the idea. So particle physicists use this concept of accelerator to see more and more inside the particles. And the idea is that we can probe smaller and smaller distances proportionally to the energy that we have to smash particles against each other, okay? So this is the idea. And I like this quote by Teilhard de Chardin, who says, "The history of the living world can be summarized as the elaboration of ever more perfect eyes within a cosmos in which there is always something more to be seen." And that's the idea as well when you try to look small, not only when you try to look big, okay? And we will see how the two things are quite related to each other as well. Okay, so what is my job as a phenomenologist? So I'm here in between. So we have experimental observations at these powerful colliders, and then we have the theoretical models. And I'm here, trying, like these guys, to make sense of what we see and interpret it, like comparing to the models that we know. Okay, so this is what I'm doing. So let me take you into what are the experimental observations and what are the theoretical models. So the experimental observation, let me take you to look at this video that was made at CERN to make you understand what happens really. So at CERN there is this big, large hadron collider, which is the biggest particle collider we have had so far. So let me take you down there to see what happens. So as you can see, each one of these lights is a beam of protons, which is extracted from atomic sources. And then these protons are accelerated at larger and larger speeds by these very powerful magnets inside these rings until they reach the big rings of 27 kilometers, and the two beams of protons are sent like in opposite direction, and they are inside this tunnel that you see here, where you really basically have like zero absolute temperature, so that there is no interaction before they reach the collision point. So you see, these are the protons. This is a spoiler. Protons are not elementary. They're made of quarks. And when one proton comes on this side and the other proton comes on the other side inside this big detector, what happens is that out of two protons mashing against each other, you have a huge number of particles coming out, okay? So really, this thing, every time, when you have billions of events per second, it means that this detector takes billions of pictures every second. In fact, we have to decide what is the interesting thing we want to observe, because if they were recording everything that happens when two protons mash against each other, there wouldn't be enough computing power in the world to ever store all this data. So basically, two protons mash, you see really relativity and quantum mechanics at work, because from two particles you have much more mass than what you smash, because the energy of the colliding protons makes up mass, makes up more particles. So 1 plus 1 equal to 300, okay, whatever. And then you see also quantum mechanics, because every time something like that happens, there is a probability that something happens. So it's not always a deterministic outcome. The outcome depends on the specific event you're looking. So this is just an example. This is a nice reconstruction that the experimentalists do. So from two protons here, what they observe is, the thing that they color in red is what is called the muon, which is like the heavier cousin of the electron, okay? And then from here, they observe like two powerful rays of light, so two photons. And here, there is a big mess, which is what I'll tell you later, which is like these little quarks that come out of the proton and they become other things that are still made of quarks, okay? So imagine that we have million of events collected per second, and we want to make sense of these events, of the probability of this to happen, and compare them to a model, okay? So what is the model? The lucky thing that we have in physics anytime is that there is something complicated, but we can split it up in bits that we do understand, okay? This is the magic of what happens at the Large Hadron Collider. So a signal that is a mess can be split into two parts that we kind of understand. Okay, so what are the two parts? So the idea is that you make a nice drawing. This is called Feynman diagram. So each of the proton is this big blurb over here. And you say, actually, the proton I know is not an elementary particle, is made of quarks that are glued together by what we call gluons, the particles that are the carrier of the strong nuclear force. And actually what we know is that the protons are funny creatures because they are not always the same, because of the quantum mechanical natures of protons, depending on the energy at which we observe them. So the energy at which we smash them, there is more and more stuff happening inside the proton, okay? So the protons are not just two up quark and one down quark, as you studied in nuclear physics. There is a word inside the proton, because as we look at them at very high energy, there is a sea of particles and antiparticles that are created inside the proton. And more gluons are there to bind all of this stuff together, okay? So protons are actually made of things that are even heavier than the mass of the proton, because when you look at them at a higher energy, it's as if their actual mass is larger than the 1 GeV that we know them to have. So anyway, but despite this complicated quantum word, which is each of the proton, we can calculate this probability. So what is the probability that a given elementary constituent, so either a quark or an antiquark or a gluon, carrying a fraction x1 of the proton energy, or the proton momentum, smashes against another constituent carrying a fraction x2 of the other proton's momentum at the time of the collision. These are things that we can calculate partially from the theory and partially extract from the data as a very complicated inverse problem of extracting functions from a finite set of data. And that's what I do for a living. That's part of what I do for a living. But that's not enough. So we need something else. We need this other part. And what is it? This is really what a theoretical particle physicist does. Okay, so you compute the scattering probability of this proton constituent. So in this case, you see a quark coming out of a proton and an antiquark from another proton, generated some final state. So in this case, you have something coming in, something else coming out, okay? So you have, in this case, quark, antiquark. They annihilate into one of these guys that I call Z or W, which are the carrier of the nuclear weak interaction. And out of it, they generate one of these carrier and the Higgs boson, okay? So this is a final state that out of this very complicated thing that they observe, they reconstruct that this is what happened in 1 out of the million of collisions that happened that particular second, okay? So that's what we do. And this thing is something that we can compute. If we have a model, which is a particular quantum field theory that works, okay? Then, given the model, we draw these nice little diagrams, and from these diagrams there are some rules that allow us to compute a number, okay? So a theoretical prediction for this thing to happen given an initial state, okay? And the model that we have, the model that we trust, because we have verified it to a very, very, very high precision, is the standard model of particle physics. You might have already seen it in some of the talks that were here before mine. Let me just tell you, so these are the particles that make up matter, okay? So matter, as we know it, is made of quarks. So as you recognize, up, up, down, which in nuclear physics make up the proton, but we have more nucleons, things that are made like the protons, that also include the strange quark, the charm quark, the bottom quark, and the top quark, okay? So these are the 6 different quarks. And beautifully, in a very beautiful symmetric way, we have the family of leptons. So we all know the electrons, okay? And and then there is the heavier cousin of the electron, which is the muon, and then the heavier, which is the tauon, and each of them has a neutrino particle associated, which lives in this weird marriage with, each lepton, okay? And this is the matter. So matter is made of fermions, which are spin 1/2 particles, okay? And then how do they interact? They interact via the exchange of spin 1 particles, which are the bosons. So the ones that we know best is the photon, because the light we have around is made of photons. Anything you use, all the electromagnetic radiation is made of photon. But there are also the Z and W, which are the carrier of what I said before, the weak interaction. And there is the gluon, which is the carrier of the strong nuclear interaction, the one binding together the protons and the nuclei, okay? And then here, there is our friend, the Higgs boson, which I will tell you more later, okay? So this is, if you want, the model that we use to make prediction. Very good. And how have we verified the content of the standard model? This is a very nice picture that I found on the Economist website. So here they said, so for all the particles that you see in this diagram, you see that many of them were modeled before their discovery. And here there is the time between the time when someone had the idea of this particle should exist and the actual discovery. So you see, in some cases, we have been surprised because the particle showed up without being announced, okay? So, for example, this is the case of the muon. Nobody thought that the muon existed until they saw something that was like the electron, but was heavier than the electron, okay? So there are cases in which the experiments comes before the theory, but there are many cases in which the theory comes before the experiment. And this is something that always fascinated me. In particular, the Higgs boson was the one that has the longest span, okay, between the time it was theorized and the time it was actually found. It was nearly 60 years, okay? So Professor Higgs, Braut, Englert, and there was a group in the US, some Belgian, and Professor Higgs in Edinburgh who had the idea, and it took a long, long time to discover it. Okay, but finally, on the 4th of July 2012, the Higgs discovery was announced, and that was a very big moment. It was a big party at CERN. Professor Higgs was there. He was very moved that finally, after giving a talk, My Life as a Boson, for many years, he could say the boson exists and it's here. There was Professor Englert next to him, and there were so many people camped outside the auditorium at CERN, all celebrating. So it was a big news, but why was there so much excitement about the discovery of the Higgs boson? So it was on all the newspaper. Okay, first of all, because it's the first elementary particle that was discovered in the 21st century, which at least for us is very nice, okay? But then I think also from a sociological point of view, it was really a colossal effort of tens of thousands of experimentalists and theorists from all over the world that got together to search for something which, if you want, is useless, but in the end it gave rise to so many useful discoveries, okay? So that's amazing. And it went beyond all conflicts and wars, so it was something very moving, if you want. And then it was really the last missing piece of the big jigsaw puzzle of the standard model, and was found 50 years after its existence was hypothesized, okay? So, fine. Why did it take so long? Why did it take more than 50 years to actually find the particles? I tried to tell you 3 reasons. that are the real reasons why it took so long. So the first thing is because the theory did not give guidance on on where to look for it. So what was the mass of the Higgs boson that physicists should have looked for, okay? So we only had an upper bound to some mathematical observation, and we had a lower bound because people at the collider before didn't find it, okay? But it could have been anywhere. In fact, there was this paper that was really funny, and thanks God people did not follow the advice of this paper. We apologize to the experimentalists for having no idea what is the mass of the Higgs boson. We do not want to encourage big experimental searches for the Higgs boson. Then fortunately, experimentalists did not take the advice, and they did go to look for the boson. Then the second thing is because, again, let me draw another Feynman diagram that I like very much. So to create a Higgs boson, the Higgs has to couple to one of the particles of the standard model, okay? It means that the probability of creating a Higgs is proportional to the coupling of the Higgs particle to the particles of the standard model, okay? And the problem is that the particles of the standard model are rather light. So the probability of creating a Higgs is rather small, okay? So out of a billion collision, you produce the Higgs only one time, okay? So the cross-section for the production of the Higgs is 10 to the 9 times smaller than the cross-section for something else to happen, okay? So it doesn't happen very often, okay? And then the third thing is the following, that not only the Higgs, the production of the Higgs happen, if you want, rarely as compared to other things that happen, but also the Higgs dies immediately into something else. So the detector will never see the Higgs boson. So nobody will take a picture of the Higgs boson because it never reaches the detector. It doesn't fly for long enough to reach the detector. It dies into something else, okay? And this something else that the Higgs boson dies into, these are very messy final state. So the cleanest final state, and this is why the experimentalists were looking for the Higgs there, was this photon-photon final state. It means that you create a Higgs, and then the Higgs dies into powerful rays of light, okay? But as you can see here, the probability is yet 10 to the minus 3. So you have a factor 10 to the minus 9 plus a factor 10 to the minus 3, because you're looking for a specific channel in which the Higgs decays, okay? Very good. But this is what happened. Look, so this is a film, is the actual discovery. So it took 2 years of collecting pictures of rays of light, okay? So that's the idea. And this is the nice thing. After 2 years of collecting pictures of the rays of light and making a histogram where you say, what is the mass of the rays of light that I'm observing? They saw this bump, okay? So this is the thing that experimentalists were celebrating. What is the bump? So the blue line you see here is an example of background, because 2 rays of light can be created without a Higgs. Anything else can create 2 big rays of light. For example, if you have quark-antiquark annihilation, they can die into 2 big rays of light, okay? But there is also the signal, okay? So in the case in which you create a Higgs boson and then the Higgs boson dies into the photons. And this is the bump, okay? So the idea was that there was an observation of the signal that was highlighting the presence of the Higgs boson on top of the expected background, okay? So in a sense, when we are saying we look for new particles, we are looking for new bumps, okay? That's what we are trying to find. Very good. So, amazing, we found the Higgs, and not only we found the Higgs, but that's a very complicated plot. But basically, what I would like you to take home is that, we have done, experimentalists have done a lot of measurements, because they smash proton at 7 TeV, 8 TeV, 13 TeV, so we have a lot of events that have been taken at different center of mass energy. And the gray is the theoretical prediction for these final states to be produced. Okay, for example, this is my best prediction for ZZ boson to be produced. This is my best theoretical prediction in the standard model for whatever, a Higgs to be produced. And these are the measurements, the bars. And they're spot on the theoretical prediction, which is amazing, because you say, wow, we've been so cool. theory has advanced really to a level where we can make amazing prediction, and these amazing predictions agree with all the experimental observation. And this is, on the one hand, amazing, but on the other hand, it means that we haven't found any strong evidence of disagreement between the standard model and the experimental prediction. So the question is, new physics, where are you? So first of all, because somehow before the LHC started, everyone thought that, wow, you turn on this big accelerator at such a large energy, and we are going to find something immediately, okay? And this thing did not happen, okay? So we are in a situation where nature is really ironical, it's very funny with us, okay? So they say, you thought you were finding new physics immediately? No, I make your life more complicated, but still, we keep looking for it. Why? That's the question. So is the Higgs the end of the story? And we know that the answer is not. So we know that there is new physics. Why? First of all, because in the standard model, when I mentioned the diagram of all the particles, I didn't mention any gravity. But we know that gravity is a force, and is a very important force. So, and gravity is not unified in the standard model, okay? And we know that if we go to the Planck scale, okay, so which is the energy scale at which gravitational effects are dominant as compared to the other interaction, there must be a quantum description of gravity, okay? And if you try to make a quantum description of gravity, you must introduce new physics. The standard model is not enough, okay? So definitely somewhere between where we are and the Planck scale, there is something. But if you notice, there are 10 to the 17, so there is many orders of magnitude between that. So new physics scale could be anywhere between the LHC scale, which can go up to 10 to the 4, let's say, and the Planck scale. We have reasonable expectation that it cannot be too large, okay, for several reasons, and I'll tell you in a minute. And we also know that none of the particles that I showed you earlier, none of the matter particles, so they only make up 5% of the whole universe, okay? So even the most recent measurements from the CMB, they show that 27% of the matter in the universe is made of dark matter, and none of the particles in the standard model can be a good candidate for dark matter. And also there is this dark energy, which is a different kind of force, which is none of the forces that we know, okay? So definitely there is something beyond. And also there is this other weird thing that, so at the beginning of the universe, there was a little asymmetry that happened. So as I told you before, energy creates matter in pair. So every time you have, for example, two big rays of light at very high energy, they produce a particle and an anti-particle, okay? In principle, if matter and antimatter recombine, there should be nothing left but energy, okay? And instead what happened at the very beginning of the universe is that every 10 billions of antimatter, there was 10 billion plus one particle of matter. So there was this slight imbalance towards matter. And that's why the universe that we know is made of matter, and it is very expensive to make any antimatter artificially on Earth, okay? Very good. So how comes? If we have some imbalance predicted by the standard model, but it's not enough to explain the imbalance that made the universe exist, okay? So that's the other thing, that there must be something that we do not understand, something we don't know that explains that. And then finally, this is a bit complicated, but I think it's important because the Higgs itself, because it's the first spin zero elementary particle, is different from all others. It means that the Higgs is very sensitive to new physics. So new physics can easily couple to the Higgs. And it has some virtual quantum effect that requires a huge fine-tuning to be cancelled, okay? So for the Higgs to have the mass that it has, we expect new physics to be not too large, otherwise it would be such a level of fine-tuning at the level of the constants that regulate the universe that would be almost unbelievable. Okay, so again, but this is our own theoretical presence. Reality might be different from what we would like it to be, all right? But anyway, we have theoretical reason. That's why we say the Higgs is a portal to new physics, because of its spin nature. Okay, and the other thing which is really cool is that the very value of the mass of the Higgs and the mass of the top is what determines the stability or the metastability of the universe. So whether, you know, this is the famous whatever, I don't know if you've ever seen it, but it's the Mexican hat that sometimes they show when they tell you the Higgs. If, you know, the Mexican hat could go up or could go down, and this determines whether eventually the universe could quantum tunnel into a different universe, and this crucially depends on the teeny tiny decimal place of the Higgs mass. Okay, so that's a very interesting thing. And the other thing is that, you know, the Standard Model is a very peculiar theory because it has only one Higgs. But there are theories that people were betting their lives on, for example, supersymmetry. I remember when I was a young PhD student, I was going to conferences and people were saying, if supersymmetry doesn't exist, we are going to resign from our job. They didn't do. But people were really convinced that supersymmetry was a much cooler version than the Standard Model, because every particle has a superparticle that is the partner, so every fermion has a boson, every boson has a fermion. And in this theory, that is, if you want, is more natural than the Higgs, and it's nice because it matches string theory at high energy. There should be 5 Higgses, okay? So if we see more than one Higgs, if we see another bump and it looks like a Higgs, it will be very exciting because it points towards something beyond the Standard Model, okay? Very good. But how do we know? How do we identify the right new physics model? So it's as if we are at a horse race where there are a lot of different models that people are betting on depending on their theoretical preferences. So how do we understand which one is right? So I just mentioned Technicolor, composite Higgs, extra dimension, supersymmetry, but there are many more, okay? So there are model builders whose job is to create models, okay? So, and how do they do that? How do we understand which bumps we are trying to find, okay? So I want to tell you there are 2 ways, okay? So I tried to split this strategy to search for new physics into 2, if you want, orthogonal direction. On the one hand, the direct searches, which is like when you observe the sky and you see a new planet, so you directly see something new, okay? And that would be if new physics was kind enough to be there, so that as we are now increase the energy, we can see a bump. This would be the idea. So direct discovery would be like finding a bump, okay? And observing the bump, we understand what new particle causes it, okay? It would be exactly the same paradigm as the discovery of the Higgs, okay? But there is also a different way of looking, which is indirect search. It's like, for example, when, you know, Neptune was not observed directly, the existence of Neptune was inferred because of the trajectory of Uranus, okay? And that's why, in the same way, you know, maybe new physics is not so kind to show up directly at colliders. It might be beyond the scale, the energy that we can reach, but there might be some sign in the tails of the distribution that show us that there is something lying beyond, okay? And I want to tell you, so basically, my talk would like to conclude with presenting these 2 mathematical concepts that help, on the one hand, in direct searches and on the other hand, in indirect searches. So this concept of symmetry and the concept of effective theory. So let me start with the concept of symmetry. So first, what is the concept of symmetry in geometry? That's something that we all understand. So for example, the most symmetric solid is a sphere. And the sphere can be defined as the solid that looks the same no matter at which angle we look at, okay? So this means that if I write down the equation of a sphere, it doesn't have to depend on any angle, okay? And in fact, it doesn't, okay? Then we have the genius, Emmy Noether, who had this idea of what are symmetries in nature? So if we go beyond, you know, the idea of just geometrical idea, the symmetry is an invariance of the laws of nature under some transformation, okay? And it was really the great mathematician Emmy Noether who understood that what we call symmetries that now we classify as global space-time symmetry correspond to the conservation of a physics quantity. For example, if I'm here and I drop a pen or if I go here and I drop a pen, the same thing will happen. This is the invariance under physics law, under translation, okay? So space translation doesn't change the laws of nature. And this corresponds to the conservation of the momentum, okay? Or if I do this experiment in 3 minutes, the outcome is still gonna be the same. This is time translation. And the fact that the laws of nature are invariant under time translation corresponds to the conservation of energy, okay? So this is a simple but revolutionary concept that we can extend to more complicated things, which is what we do in theoretical particle physics. So first, imagine that now the translation is no longer a global translation, but it's a translation that depends on the specific point in space and time, okay? So if you have a straight line over there, and you transform it under this local space-time transformation, so local because it depends on the point in space and time, then this line would become some curved line, okay? And now you ask me, what are the dynamical equations that are invariant under this transformation? And these equations are the equation of general relativity, okay? Then, let's do something even more complicated. Now let's think about local internal symmetry. So in symmetries that do not depend on the space-time, but on some so they depend on the point in space-time, but are not space symmetry. These are rather some internal symmetries. I tried to give you this example that my colleague taught me. So each of the quarks comes in 3 identical copies, okay, in our theory, because you always write it in 3 copies. And we label each of these copies by a color. So we say there are the red quark, the green quark, the blue quark, and they're all the same, okay? It's just a label. We like the color. We could have chosen something else, whatever. And the rotation of the quark colors into each other, so if I swap the green and the red or the red and the blue, is a symmetry of nature. So if I write the law of the strong interaction, nothing changes when switching this kind of stuff, okay? Go back to Emmy-Noether. What is the conserved quantity that corresponds to this invariance under rotating the quark? This is the color symmetry. Very weird. But then I say, now if I ask that this invariance under quark switching happens at each point of space and time, I must include in the theory the gluon, okay? So it's not that people invented the gluon out of the blue. Gluon had to be there, and they had to glue together the quarks. Otherwise, this symmetry would not yield, okay? So it's a very complicated concept. It took me 3 years to understand it, but I just summarize it in 2 minutes because I'm very kind to you. But the idea is that the local internal symmetries are the ones that dictate the particle interaction and the particle content of the theory. So what do model builders do? They say, wow, let's imagine that there is a bigger symmetry, more than the switching of the quark colors, okay, that embeds the symmetry of the standard model. If I postulate that, I can tell you what are the new particles you should look for, okay? And that's exactly what they do. So let me go back to the picture we had before. So the color symmetry, the one about the quarks that I tried to tell you now, then there is an electric charge symmetry and there is an isospin symmetry. I don't tell you what they are, but anyway, this is the gauge symmetry of our model. If you impose this gauge symmetry, then the gluon, the W, the Z, the photon have to be there. Okay, so I'm not free to put any particle I like. Once I decide the symmetry, the particle content is deterministically determined. Okay. The Higgs is another story. The Higgs comes from a breaking of symmetry. It's a very complicated thing, but still it's symmetry, okay? So what people do say, wow, I want to make a broader symmetry, like supersymmetry. In fact, that's why it's called super, because it's bigger than the standard model. So you have, and then you have extra dimension or great unification, whatever. So this is a bigger symmetry that embeds the symmetry of the standard model. And this tells you what are these new colorful particles that I made here, okay? And then people look for bumps. In fact, there was a big excitement at some point 3 years after discovering the Higgs, because it seems that again in the same channel where the Higgs was found, which was the photon-photon, there was this bump that you see was around 750 GeV. So it was 5 times heavier than the Higgs boson. And this seemed to be some of these new particles. So the people who invented the model that made sense of that bump, they were very excited. They thought they were going to get a Nobel Prize. But then this was just a statistical fluctuation, okay? As more data were collected, this bump faded away, unfortunately. But that's the idea, you know. So people say, okay, this is my new symmetry. These are the particles. These are the bumps you should look for. And if you find this bump, I'm going to get a Nobel Prize, okay? That's a simplified version, but that's what happens. Okay, what is the other way? So what if nature is not kind enough to put one of these new particles into the realm of what can be understood? And now I take you to another difficult concept, but I think it's nice because it shows, at least it gives an intuition of the power of maths on how we move around. And this is the concept of effective theories, okay? So imagine you have a new particle that is much heavier than the energy of the colliding proton, okay? And remember, E equal to mc squared, okay? So you cannot create it unless you have an energy that is at the mass threshold, okay? Good. So then it means that when you write your beautiful quantum field theory, you can integrate out the particle, okay? So what happens is just that you integrate out the particle and you're left with the effect of that particle, which is a new interaction between the standard model particle that is not in your standard model, okay? So that's the idea. This is a bit like the Fermi theory. For those of you who know it, you know, is like Fermi understood well the radioactivity, so the beta decay, whatever, because with the model that was like that, and then actually when they discovered the W and the Z, they discovered that the Fermi theory was just an effective field theory of something bigger, okay? And now we do the other way around. We say, okay, what if there were heavy particles? We would integrate them and we see some new interaction. The good thing is that we can parameterize. I don't tell you how, sorry if I put an equation, but I like equations, okay? So this is how we can parameterize them. We write the standard model, and on top of it, we write something which is some coefficient divided by the mass of this new particle. So something that suppresses the presence of this thing. Okay, so and then we understanding that we want to understand what is the particle that causes this deviation, this new interaction. This is a bit of the standard model of a tidy room, and then you have a deviation from the standard model of a tidy room, okay? And then you ask yourself, what is the thing that caused this deviation from the standard model to non-standard model? And the explanation is very simple. My daughter came home from school and spent 2 hours in her room. So in this case, what caused this shift from the expectation is very clear. But in particle physics, it's not so clear at all. So what we try to do is that we have experimental measurements, standard model prediction, and we parameterize the possible deviation due to these new heavy particles by some specific parameterization, okay? And this is a cartoon that explains things. So we have the current measurements and we keep measuring things, and the theoretical prediction are the blue dots, okay? So imagine that, so each of these deviation is not a bump. So each of these deviation is not significant that tells you, wow, we found a new particle, okay? But you see a tiny thing that is not right there, another tiny thing that is, not right there. And then what you try, the idea is that by observing a pattern in all of this deviation, it's as if these effective theories are like a telescope. They tell us that we would see the effect by observing the deviation that this new particle induces. Okay, so we can see farther in energy by doing that. So what we try to do is that as we have more precise data and more precise standard model theoretical prediction, we want to identify pattern of small deviations. And from a pattern of small deviation, go up to what I call the UV, which is the scale where this particle could actually live, okay? And this is really crucial because if you want to plan for new experiments, for new colliders, this effort is very important because it tells us where is it that we can expect to directly observe what this telescope of effective theory is just pointing us towards, okay? So this is a very interesting plan. And, and that's what experimentalists and theorists are doing. For example, I don't even know what it is, but it just shows that, clearly the standard model is there if all these coefficients are equal to 0. So, and you can see that from these, again, this is the famous gamma-gamma, okay? So from proton-proton to 2-photon, the standard model clearly is a good fit to the data. So it's something that explains the data really well. But there is a big region in the parameter space where all these coefficients can be different from 0, okay? And this explains the data well as the standard model, okay? So the idea is that there is much more in the universe than what we can observe. And we are trying to restrict this space so that we have a kind of smaller range of possibility of what things can be observed. Okay, so I would like to conclude with this sentence that great discoveries like the Higgs boson, which seem to mark the end of the story, mark in fact the beginning of a new, more extraordinary one. Because with so many data that have been approved collision to go on for 20 more years and more precise observation, I think that either a bump or some pattern of deviation can be observed, and definitely might be some surprising discoveries just behind the corner. Thank you very much.